Yes, so I hope, yeah, it's actually quite a pity not to be in Les Houches. I was actually looking forward to start traveling again, but as we all know, this has not been possible. So I'm happy to be able to give the lecture nevertheless as an online lecture. So I will go pretty slow, and I will probably repeat many things you know already, but hopefully there will be also something new for all. And of course, you are welcome to stop me at any moment if you have any questions. I have to say, unfortunately, I don't see directly the chat because my screen is all taken by the slides. But in case you can, of course, stop me also by voice, or I can also look at the chat at the end of the talk, or if you really think I can also do a break in between and try to answer questions if anybody tells me that there are a lot of questions to answer. Okay, so I've been asked to cover a little bit the cosmological motivations for the search of neutron EDMs. And I will start pretty slowly, as I said. I will give you a little bit an introduction to CP evaluation in the standard model and EDMs. As I said, this is probably something you already know, but just to put everything in the context, since I am also the first lecturer in these lectures. And then I will cover the two directions which are tightly connected to cosmology and CP evaluation. On one side, I will discuss a little bit baryogenesis in the standard model, and then the electroweak baryogenesis beyond the standard model. This is one of the part where you have actually a direct connection to CP evaluation and additional sources of CP evaluation, which can play a role also in electric dipole moments. Actually, I had a part on leptogenesis and CP evaluation in the leptonic sector, which at the end I decided to cut out. Sorry, I didn't change the outline. If you have any questions about that, we can try to cover it at the end. Of course, in that case, the direct connection to the neutron EDM is less strong, but of course you can still have a connection, for example, for the electron electric dipole. And then the other direction is connected instead to the solution to the strong CP problem via the axion. The axion can be then a dark matter candidate, and this is the direction that also give you quite a tight connection between CP evaluation and cosmology. And we will discuss a little bit what are different scenarios with the axions as dark matter. Of course, there is also another thing which I added at the end. Axions could also, in principle, act as a source of baryogenesis. So this is another direction which has been started recently by different groups. And this, in that sense, would also be along the line a bit of Affrechtine baryogenesis, if you know. And this is one thing I will try to cover at the end, if there is any time left. And I will conclude. Okay, so let me go to the introduction on CP evaluation in the standard model and the electric dipole moments. Now, CP evaluation is part of a bigger set of symmetries in the standard model, which are C, P, and T. And CP and T are actually discrete symmetries, since you are, in this case, not doing an infinitesimal transformation, so you don't have any small parameter, but you have practically a discrete change. In particular, charge conjugation symmetry just changes the particles in the antiparticle. If you want, the other P and T symmetries are connected to a change in the sign of the space variables or the time variable. And due to this change, for example, in the case of spin, you have also a change of the spin, because parity in some sense is again, if you want, the spin remains the same, but the projection of the spin on the space variables actually changes due to the change in the coordinates. And these three symmetries are actually one of the basis symmetries we have in our theory. In particular, here I give you the expressions for spinors. Of course, spinors are very important in the standard model. And in the case of spinors, we can realize this transformation here very simply by the use of particular gamma matrices. So the gamma 2 in particular connected to the charge conjugation symmetry. And otherwise, as you see, parity symmetry, we change the right-handed and left-handed fermions in each other. And if you do CP symmetry, of course, you combine charge and parity symmetry. So it has the form given here, where you have, again, a connection from between the spinor U left to the spinor V right. And then the other, which is a little bit more difficult to really explain or to discuss in quantum mechanics, is the T symmetry. And this is because it has a particular property, it has to be anti-unitary. Since when you change the sign of time, then of course also in the evolution and also in the, if you want the evolution operator, if you want to see it for a free theory, it would be just exponential of IHT. In that sense, when you change the T, you have also to take into account that you have to change also some of the imaginary variables in order to be able to have a proper definition of the symmetry. So in that sense, it's all the other symmetries are realized as through unitary operators. Instead, the T symmetry has to be realized by an anti-unitary operator. Okay, now at the basis of quantum field theory, we have a very famous theorem, the CPT theorem, which was practically going back again to Pauli. We just heard about Pauli lecturing at the Alesouche school. And indeed also he and Lüders proved in 1956, I think, the CPT theorem. So the CPT theorem states that if you have a Lorentz invariant quantum field theory with an Hermitian Hamiltonian, you cannot violate the product of CP and T symmetries. And this means, of course, that if CPT is conserved, then, of course, every time you have a CP violation, you have to have the exact amount, corresponding amount of T violation in order for CPT to be conserved. And of course, CPT, the proof of the theorem is quite complicated, and it's based actually on having the chance to do global Lorentz transformations. So in that sense, so large Lorentz transformation, so that it's in some sense, it's not completely clear if you can really extend it to the whole cosmological setting, if you want. Because of course, in cosmology, we have Lorentz symmetry only locally, and we don't have, I mean, generically in general relativity, we have a diffeomorphism invariant instead of Lorentz invariance. Nevertheless, of course, locally, we always have Lorentz invariance. And in that sense, I think it's usually not so trivial to violate CPT also in gravity setting. Generically, a consequence of CPT is the fact that you have particles and antiparticles which have exactly the same mass. And this has been also tested experimentally. You maybe heard that, I think recently also a new measurement of the anti-hydrogen atom was made, and this seems to confirm exactly that there is exactly the same mass. And but this does not mean that there are the same decay rates or the same scattering rates. And indeed, this is one of the things we will exploit later on in order to have the chance to produce a non-vanishing CP violation, and also a non-vanishing, for example, baryon asymmetry in baryogenesis. Okay. Good. So, but of course, I mean, in this lecture, I will always assume that CPT is conserved. And so in that sense, again, that CP and the T violation are related. And this is in the models I will discuss, this is always the case. Of course, you can also try to study more complicated models where, for example, you can have a violation of Lorentz invariance, and then you could also, in some sense, go beyond the CPT conservation. Okay, now another important characteristic of CP violation is that it arises just at the quantum level. And this is because usually when you look at rates for particles, so first of all, the CP property is usually connected to having complex couplings. And if you look, for example, at this very simple Yukawa coupling I'm writing here, you have a lambda h q bar u and a lambda star h star u bar q. You see immediately that you could have a lambda complex, so lambda different from lambda star. And then in principle, you have two different couplings for particles and antiparticles. But if you look at the process at the tree level, you find out immediately that, of course, the amplitude is given by the coupling, but the rates are proportional to the matrix elements, so the coupling modulus squared. This means at the end, from the side of the case where you have just Born level amplitudes, you have that the matrix element for the particles and the antiparticles is exactly the same. And so you don't see any CP violation. But of course, this is not the whole story. We have also loop correction. And for example, here is the basic process, which we'll use later on also for in general, we can use it for baryogenesis, but not, I mean, it's actually the basis of more leptogenesis, which I will not discuss very much in detail here. But nevertheless, here as an illustrative example, if you consider, for example, a decay again of the Higgs into two fermions, with a tree level is the same for particle and antiparticle. If you look at the loop processes, these loop processes, which are drawn here, both if you want vertex correction and what is called often wave function correction, so this bubble, then if you compute these two, you see that you have in principle also the conjugate coupling involved. And if you consider the amplitudes, you have to sum all together. And then when you take the matrix element and you square the amplitudes, you obtain this second term, which is a real part of a combination of couplings times a loop factor. Now, the loop factors are actually the same for particle and antiparticle, exactly because of this CPT property that the masses of the particles are the same. And therefore, if you want, the constraints you have in the momenta in the loop are exactly the same, the propagator are the same. So the loop integral just depends on the masses of the particles, and it's exactly the same function. So at the end, if you just subtract the rate for particle and the one for antiparticle, you obtain exactly this delta M, which is given here, which is the difference between the two processes. And at the end, since you have in total, this has to be real, it is actually the product of two imaginary parts. So one imaginary part comes from the loop, and the other imaginary part comes from the practically the imaginary part of the product of the couplings. And you see immediately this, if you want this imaginary part of the loop is always connected to the absorptive part of the loop, also called. So it means that in this loop diagram, some particle, at least two particles, have to be on shell. And in that sense, it's actually correspond to producing, if you want, particles on shell and physical particle, which then you can see it as a production of particle and then a scattering process, if you want. And at the same time, in the imaginary part of the product of coupling, you see that you need, in some sense, to have non-trivial phases, but that is not enough. You need also a non-trivial, very often flavor structure, because you see immediately here, if you would have only one single lambda coupling, here I have lambda, lambda star, lambda, lambda star, this is actually real. So the imaginary part will immediately be zero. But of course, in general, these Yukawa couplings are matrices in flavor space. So if you take combinations which are not, so that the couplings are not the same, at the end, you have a non-trivial phase. And if you want, you can look at it also from the unitarity relations among processes and rates. From unitarity, you see that you have a relation from the practically the transfer function for one process and the transfer function for the antiparticles. And this is exactly the relation that you see here. And the bottom relation, if you want the first part where there is this imaginary part, this is exactly the same term I gave you before. Here it is a bit confusing perhaps that here I have imaginary part and before I have a product of two imaginary parts. But here when I compute these T matrices, I am already on shell because I am summing with a, you see, you sum over F or I, and you have already in some sense that you are writing the loop as a product of a scattering and transition. So in that sense, you are already considering, if you want, the absorptive part of the loop. And if you go to higher order, of course, you have additional terms, which is, for example, here, this term T-DAG T squared. This is, of course, is higher order in the coupling, because there you would have, as usual, more powers of the coupling. So it's usually the first term, which gives you the dominant contribution. Okay. So putting all together, we can have a couple of conclusions about CP violation even without doing many computations. One thing is important, and is also important for baryogenesis at the end, is that CP violation is usually small. And this is because it's suppressed in some sense by many things. As I said, it's usually higher order in the couplings. So there is a suppression of the coupling, there is a loop suppression, and then there is also this non-trivial flavor structure. So that you usually need, for example, we'll see later on, if you have quarks, you need to add many quarks of different flavor. And this means at the end that you have mixings also that can be not only large mixing, but also small mixings involved. Okay. Now, in the standard model, this CP comes exactly due to the, well, C and P are violated, of course, due to the chiral structure of the standard model. So the electroweak interaction is practically chiral and affects only the left-handed fields. So in that sense, these breaks maximally, if you want, C and P. But it doesn't break CP as long as the Yukawas are real. So the CP violation is coming from the complex Yukawa. And these are exactly the terms I'm writing here, this lambda again, where I have the vacuum expectation value here, for example, of the Higgs, which gives me exactly the mass matrix for the quarks. And as you probably all know, you need to diagonalize this matrix, which is a matrix, as I said, in flavor space. So it's a 3x3 matrix. And you have the freedom of diagonalizing it via two unitary matrices, one rotating the left fields and one rotating the right fields. And this is true both for the up quarks and for the down quarks. And of course, also for the charged leptons, it would be the same. And for the neutrinos, it's slightly different, depending if you have also a Majorana mass or not. But at the end, the fact that you have this non-trivial rotation, of course, it does not show up if you have diagonal couplings. So for example, the neutral currents are diagonal. They have left fields connected with left fields and right fields connected with right fields. So there, of course, the mixing just disappears. But you have one case where this doesn't happen, and this is the coupling, of course, to the W, so to the charge current couplings. In that case, you are coupling the up quark and the down quark, both in the left-handed sector, but they are in principle rotated by different unitary matrices because the mass, of course, of the up quarks has nothing to do with the mass of the down quarks in principle. And this means that this rotation, U left V left DAGA, it's actually a non-trivial matrix, which is exactly the CKM matrix in the standard model. And it is, yeah, I will give you the form in a minute. It is indeed a non-trivial matrix. Notice that the right-handed rotation instead just disappear because we do not have right-handed currents. And therefore we actually lose anyway, in some sense, to have information to the right-handed about the right-handed rotation. But of course, if we had, for example, a left-right model and a W right, then of course this would be we would have in principle another matrix, another CKM matrix for the right-handed sector. Now, here's the shape of the CKM matrix. You see that it's a 3x3 unitary matrix. And in principle, you could think that you have then 3 mixing angles and 6 phases, 6 complex phases. But you have also the possibility to really absorb some of the phases into the fermionic fields. So fermionic fields appear in the Lagrangian always quadratically, and you can in some sense reabsorb phases into the fermions, in particular to make the mass real, for example. Is there any question? Okay, no, okay, I seem to have heard something. So if you can, in this case, for the standard model where you have 3x3 case, you have 5 phases that you can reabsorb, so that at the end you're left only with a single phase. And here I give you the number for a generic n by n matrix. You see that the more generations you have, the more phases you have. And the important thing, of course, is that if you would have only 2 generations, you would have no physical phase. So in principle, no CP violation. But instead, we have 3 generations, and therefore we have one surviving phase. And this phase in this Wolfenstein parametrization I'm giving you here is connected to this eta parameter, which is the only imaginary part here in the element 1, 3 and 3, 1 of the matrix. Notice here also that, as I said, the mixings are also important, and the CKM is in some sense, well, not exactly a unit matrix, but it's indeed has the bigger elements in the diagonal as usual, and the next largest element is the lambda, which is of the order of 0.2, and then all the other elements are even more suppressed. So that if you want to look, for example, at the invariant that you can form from the CKM, which is the Yarskong invariant, then you find out that this J, which is corresponding actually to the area of the unitary triangles, is a very small number. So it's a 10 to the minus 6, exactly because it has a suppression of lambda to the 6. And also it's of course proportional to this imaginary part. So if the imaginary part is 0, you would not have any non-vanishing J. And of course, the relation is here again, is J is exactly the area of this unitary triangle. So if you take the CKM matrix and you contract together 2 of columns and the rows which are not related to the diagonal elements, you will get that the product of elements is give you 0. So the sum of the different products. This means that this corresponds exactly to a triangle, and you can plot it. For example, this is one of the results from CKM fitter, where also the experimental data are given, and the constraints that you have from different experiments. And so far, we can describe all the CP violation we see in the standard model just by one phase in the CKM. And this phase is actually not very small. It's actually order 1. The smallness, if you want, of CP violation is more connected to small values of the mixings. Okay. Now, of course, in the neutrino sector, you have a little bit more freedom, as I mentioned. You have, in particular, the freedom to have a Majorana mass, for example, through the dimension 5 Weinberg operator, where in that case, you can obtain directly a Majorana mass for the left-handed neutrinos. And this is one way, for example, to give masses to the neutrinos without having addition of any other additional state. Of course, a similar thing you can obtain also by adding the right-handed neutrinos and then having a mass, a Majorana mass for the right-handed neutrinos. And in that case, you have the seesaw mechanism. But at the end, this doesn't change the fact that you can write the mixing of the light neutrinos through these Pontecorvo, Makina, Kagawa, and Sakata mixing matrix. And this is the corresponding of the CKM for the neutrino sector. And the characteristic here is that you have again 3 mixing angle, 1 phase, but you have also in front this P matrix, which is a matrix containing 2 additional phases. And these phases are Majorana phases, which are appearing only if the neutrinos are Majorana fermions. And in that sense, if the neutrinos are really Majorana, you have the possibility to have a practically larger phases in the neutrino sector and more phases. And also in some sense, also these Majorana phases can be large, so that in that sense, you can have additional sources of CP violation in the neutrino sector, which are not of the Dirac type. Okay. So let me come now, what does all this have to be with electric dipole moments? Now, an electric dipole moments, I think everybody knows that from classically is just coming from having, if you want, charges displaced or a displacement between positive and negative charges within an object. And indeed, if you compute for a charge distribution, you can compute this dipole moment just by integrating the vector r weighted by the charge distribution. Now, quantum mechanically, you can see that these quantities actually usually proportional to the angular momentum for a bounded object, for example, so that you can write it also as a constant times this angular momentum, and or spin if it is a fundamental particle. So that at the end, you have exactly the picture that you see here, which I have stolen from Wikipedia. You see that generically you have the 2 vectors which are parallel or anti-parallel. And indeed, doing a transformation like a parity transformation or a time reversal transformation is actually acting differently on the dipole moment and on the angular momentum. So you see that the parity operation changes the direction of the electric dipole moment, and the T operation changes the direction of the angular momentum, as we already discussed. And this means that at the end, you see immediately that so that you would have, if you have a presence of an electric dipole moment, this is again a signature of having either P violation or T violation. And of course, if you have T violation, you also have CP violation. So in that sense, you need to have somewhere in your theory some CP violation in order to have a non-trivial electric dipole moment. And indeed, here, if you want, you can write out actually for a fundamental particle, for example, like the electron, you can really write the Lagrangian if you want that you could correspond to an electric dipole moment. And here I'm writing the generic form of all the corrections that you can have. You have, of course, the first vertex is the gamma mu, which is the usual vertex we have in the standard model, also at 3 level. All the other terms arise only at loop level, so they are coming from radiative corrections. And here you probably recognize you have some form factor connected to the magnetic dipole moment. You have one F3 connected to electric dipole moment, and then you have even a F4, which is the anapole moment. So generically, you would assume that you could produce each of these terms from loop diagrams. The problem in the standard model is that the only source of CP violation is the CKM matrix. And it turns out that in order to produce a non-trivial electric dipole moment, you need to have at least 4 weak vertices, because if you have only 2, you actually cancel the phase at the end. And you need also a lot of quarks, because you need to have all 3 families practically involved in the diagram in order to have a non-trivial flavor structure and non-trivial phase. So at the end, you have a contribution which is very high, is highly suppressed. So I was trying to find the loop diagram to show you how complicated it is, and I was not able to really to find it. It's actually quite complicated diagram. So I guess it's probably not so instructive to see it, but it's just to say that, of course, in the standard model, you cannot generate this operator very easily. And this leads to the prediction. So people, of course, have computed this diagram already many years ago. And they found out that for the neutron, the dipole moment is of the order of 10 to the minus 33 or 10 to the minus 34 e centimeter. This means, of course, that due to this suppression, you are really the chance to find other CP violating sources giving you a larger contributions. And indeed, this is the reason why it is a very good target for exploring additional sources and the additional CP violation beyond the standard model. Now, here, of course, I am a bit cheating. And this is because I threw away actually one important point and one important contribution to the electric dipole moment, which comes from the strong CP problem, if you want, from the fact that you have a non-trivial vacuum in QCD. And you have to add to the Lagrangian to weight in some sense this different vacuum configuration, this additional term, which is called the theta term, with G, so the gluon field contracted with the dual. And this term is again a term which violates T and CP, since the gluon field strength and the dual have actually opposite properties. So if you do T change, you will have a minus sign in this operator, and also if you do a CP transformation. Of course, we know that QCD doesn't seem to violate CP, and therefore, in some sense, it's a bit of a puzzle how is possible to have such a term. I will get to that in a minute, but this is already telling you that theta probably has to be quite small. Now, if you really want to have a solution to this problem, one possibility would be to just rotate away this term due to axial U1, global U1 transformation on the quark fields. And this, in principle, you can do if at least, so you could also do it only in one field, especially if there would be at least one which is massless. So if the field is massless, then the right-handed component and the left-handed component don't practically couple through a mass term. And in that case, you can rotate them in the same way if you want through this axial type of transformation. And you can practically cancel completely this theta term. So in that sense, this term is not physical if you have at least one massless quark. Unfortunately, it seems that the quarks are not massless. We have studies on the lattice trying to see if it is possible to still have one massless quark, and they seem to deny it. So we have an electroweak, if you want, mass, or a mass coming from the Higgs mechanism, of course, for also all up and down, and so all the quarks. And in that case, of course, you can still, if you want, do a kind of global U1 axial transformation. But in that way, you can, in some sense, just rotate away also the imaginary phase in the mass and bring it together to the theta. So at the end, if you have massive fermions, what is really the physical quantity or the physical parameter is not just the theta, but the theta plus the phase in the determinant of the quark matrix. So that is the usual definition of this theta bar parameter. So theta plus the argument of a determinant of MQ. And this is indeed what I will use also in the next slide. Sorry, okay, here I forgot to put the theta bar. So, yes, so in practice you have this term with the theta bar, and this term with the theta bar, it's actually generating a non-vanishing electric dipole moment. This is because if you want, it's a practically long computation. You need to do chiral perturbation theory, transform these into, in this case, it's easier to transform this theta term into the mass term if you want. And then you can see that you have actually some non-trivial vertex for the pions. In particular, this square vertex, which I have here in the diagram, which is exactly has a, if you want, a non-trivial axial structure. And through diagrams like the one I'm showing here, where you have, again, an exchange, a loop diagram with the pion in this case, you find out that you generate actually a electric dipole moment proportional to the theta bar parameter. And this coefficient in front is not very small, it's just 10 to the minus 16. So in that sense, you see immediately that from the constraints that you all know from the electric dipole moments of the neutron, you need theta to be, theta bar to be less than 10 to the minus 10. So this is actually one of the, this is exactly what is formulated as the strong CP problem to try to explain why this theta parameter is so small. And later on, we will see a solution of it, which is to make this theta bar as a dynamical quantity. And therefore, if it is dynamical, it can relax to zero, but this will have additional consequences. So in that sense, you could, you have a way to cancel, if you want, this theta bar and avoid this contribution to the neutron dipole moment, electric dipole moment, but at the cost, if you want, to have additional degrees of freedom, which are important, especially in cosmology. Okay. So this one was a little bit the my introduction. So are there any particular questions about this? I can try to check the chat in a second. Let me see.
Can I ask one particular question?
Yes, of course.
I'm Takashi from Osaka University. About your explanation of the CPT symmetry. You mentioned that the for example, mass should be the same for the particle antiparticle, but not the decay rate or the process rate, reaction rate. And my question is about the lifetime of the particle, because I heard that the lifetime of the particle is CPT symmetric, right? Co-CPT conjugate between the particle and the particle. And but the so for example for neutron, which has finite lifetime, how does it work? You know what I mean? So
yeah, you mean no, well,
yeah.
the decay rate does not have to be equal. So the decay rate, of course, fixes also the lifetime. So also the lifetime doesn't have to be absolutely equal.
So okay, the lifetime of the particle antiparticle is not actually CPT conjugate, you say?
No, because it's if you define it as from coming from the decay rate, it is not. So the decay rate,
Okay.
of course, in principle, you could sum it up and consider all possible contributions. But I think in general, yes, if you define it from the decay rate, it's not exactly the same.
Okay.
Of course, the change, I mean, this is what happens, for example, in leptogenesis. Of course, in that case, the same particle decay into particles and antiparticles. So if you compute the total decay rate, is actually it's the same, because the particle is its own antiparticle. But of course, the decay into the different channels is not the same. So, for example, you would have a right-handed neutrino decay into leptons with a rate which is slightly different than the decay into antileptons.
Okay.
Yeah. And for example, also in the B sector, you can see immediately also in the B sector, you have different decay rates for different channels.
Okay, thank you.
So it's similar.
Thank you.
Yeah, you're welcome. So more questions. Okay, again, I'm not able to see the chat, unfortunately, but I guess that there are no urgent questions. Otherwise, just let me know. Let me see. Yes, now I can open the chat. Okay, I see there are messages, but there is no question at the moment. Okay, good. So then we can go on to the next part, which is connected to the baryogenesis. Let me go back to the appropriate slides and I start again full screen. Okay, so now, of course, I concluded here saying that there is this possibility, of course, of having CP violation in the EDMs. And of course, one reason why we want to have additional CP violation, apart from the standard model one, is connected to cosmology, at least in cosmology, is baryogenesis. Indeed, we see practically here is the usual pie chart of the universe compositions. We see that we have actually just a very small fraction of baryons. This is approximately 5% or so. And of course, a lot of unknowns like the dark matter and the dark energy. And the problem is to understand why we have so many baryons in principle, because we could have even less. Of course, the baryon density is also one of the key elements to compute the abundances of the light elements from Big Bang nucleosynthesis. And also from there, we can estimate what is the value. And again, if you use the parameter omega h square, which is the density rescaled by the critical density, you get something of the order of 0.02. So it's approximately 5% we had before. Indeed, CMB and nucleosynthesis give you more or less the same value. And I have here one of the slides telling you, of course, the CMB nowadays is the best measurement we have to compute the value of the baryon asymmetry. You see here that the height of the peaks really depends quite sensitively to the value of this eta parameter, which is the baryon asymmetry. So even a 15% change, as you see here in this plot, will bring you up or down depending on and practically give you a deviation from what we see. And indeed, here there are some of the plots and the constraints from Planck. And you see here, for example, that you can nowadays also do fits relaxing other parameters. For example, the number of effective degrees of freedom, which counts the relativistic species, or even the density of helium, this YP parameter. And at the end, you find, as you see, these curves are always crossing this green line, which is the prediction for standard BBN. So far, we seem to have everything in agreement. There were, of course, probably you're aware, some discussions early that CMB could also be allowed to have a little bit more relativistic species than just the 3 neutrinos, but at the end is it's not a very strong signature. So in that sense, you are compatible with the usual standard model numbers. And notice here, of course, again, that the CMB and the nucleosynthesis are in some sense a bit orthogonal in parameter space. So they are measuring, of course, this quantity also at different epochs. And they are both giving us a very good estimate of the baryon asymmetry. So at the end, the reason now is to try to explain why this number is what it is. And one possibility would be to consider just that you have baryonic matter, which is in equilibrium and stays in equilibrium as much as possible, and without having any asymmetry. Now, if you had that picture, then in some sense you would have a so you will have a decoupling, if you want, of these baryons in a similar way that you had for example, for WIMPs. So the particle will stay in equilibrium as much as possible. And since they are interacting strongly, you have actually that they will keep in equilibrium very long, so long that the density would be, as an estimate, a rough estimate, more like 10 to the minus 10 instead of 10 to the minus 2 in omega b. So the only way to avoid these decrease of omega b would be really to avoid the annihilation of baryons and antibaryons together. So you would need really to separate the baryons from the antibaryons on large distances of the order of the Hubble size at the time of the coupling. And in that case, at the moment, we don't know any mechanism would really be able to separate, if you want, baryons from antibaryons from in the thermal plasma from such high distances. So in that sense, the way out is to assume that you have an asymmetry in the thermal bath. And if you start with an asymmetry component, then these will actually stop, if you want, your particle from annihilating further once you reach the value which is equal to the asymmetry. So in that sense, you do not follow anymore the equilibrium curve up to very, very small densities, but you are, in some sense, there is an obstruction due to the presence of an asymmetry, as long as you have, of course, no more processes which can violate the baryon number active in the plasma. Yes, so this is exactly what we call the baryogenesis, the way to produce an asymmetry into the baryons in such a way to explain why we have a 0.05. And in that sense, this is the way to produce an asymmetric universe from asymmetric one. And this is has a long story, and actually Sakharov in 1967 was the first to write down really the conditions you need to satisfy to produce a baryon asymmetry if you start from a universe which is symmetric. And he immediately realized that you just don't need just B violation. Of course, baryon number violation would seem to be natural because you need to produce a net baryon number. But you need also C and CP violation. And this is a little bit more subtle. But the point is, if you do not have C and CP violation, you would produce matter and antimatter with the same rate. So even if you have B violation, you would produce the same number of baryon and antibaryon. So at the end, you would again have a zero net baryon number. And the third condition he also identified is that you need also departure from thermal equilibrium. And this one you can see in different ways. One way to see it is that in that sense, thermal equilibrium is the state of maximal entropy. And if you want the maximal entropy is, as long as you can, if you can change the baryon number, is actually for baryon number equal to 0. And therefore, if you would have a B violation in equilibrium, at the end, you would erase the baryon number, even if you start with some. And on the other hand, you can also look at in the other way from the CPT theorem, if you want. If you don't have a violation of T, also your violation of CP at the end on the thermal bath will again average out in some sense. So if you don't have a kind of time arrow, you are not able to generate a baryon number. Yeah, but then it was realized that actually in the standard model, what you have is actually that the B plus L symmetry is anomalous, and you have a B plus L violation in the standard model itself. So in that sense, you can actually rely on this B plus L violation perhaps to produce a baryon number. Or otherwise, if this B plus L violation is really in equilibrium, it would tend to erase the B plus L number. And this violation is again connected to a non-trivial vacuum structure of the electroweak sector, in this case, not the QCD sector. And in that case, again, you have different vacua with different baryon and lepton numbers. So if you want, you change when you move from one vacuum to the next, you change B plus L by twice the number of flavors. And you have two ways to change if you want to move from one vacuum to the other. One, of course, if you are at T equal to 0, so you have no possible thermal fluctuations, the only way would be to tunnel from one vacuum to the other. And this is a process which is very, very strongly suppressed. The rate is suppressed by the exponential 1 over the gauge coupling of the electroweak sector. And this is a very, very tiny number, so that indeed also nowadays we do not observe these processes near anywhere in some sense. So we have practically in the standard model, we can say that B and L are conserved, even I mean, even separately in that sense. And then we can, though, in the early universe have also thermal excitations. And if we have temperature, so T greater than 0 and thermal excitation, we have also the chance to jump above the barrier, if you want. And this is what is called a Spaleron transition, because the configuration which brings the field from the vacuum to the top of the hill is called a Spaleron. And these transitions are not suppressed if you have a sufficiently high temperature. And this, for example, is the rate which I am writing here, this gamma. This is the rate below the electroweak phase transition, which is still, as you see, if you have a temperature of the order of the electroweak scale, these actually will not be suppressed. And even better is above the electroweak phase transition. There, the spalerons are not suppressed by any mass of the gauge boson, etc. So there you have really equilibrium. And in that sense, having equilibrium again would tend to erase this B plus L number. And the only way in some sense you can keep something surviving below the electroweak phase transition is in the case where you have a non-trivial B minus L number. Because of course B minus L is not changed by these transitions. So if you start with a non-trivial number, this will be conserved all the way until today. And at the end, this will give you a net baryon number and of course a lepton number. And here I give you the expression for the baryon number, which is thus proportional to B minus L, weighted by quantities which depends on the number of flavor and also the number of Higgs fields you have in the thermal bath. But this number here, this prefactor is something of the order 1/3. So the order of magnitude is the same as the B minus L number. And in that sense, this is the big advantage that you are also able to produce a baryon number also starting from a lepton number, because of course you could produce a B minus L starting from a leptons. And this is exactly the process which is called leptogenesis, for example. This is one of the advantages of having these B plus L processes, which in some sense move around lepton and baryon number and allow to have at the end, as I said, a baryon number also from lepton number. Now here just a picture of these sphalerons processes. Of course, as I said, in these electroweak sphalerons, you have in principle both leptons and quark involved, so that you have B minus L conserved. So in some sense, you see it's a kind of a big process involving a lot of quarks and 3 leptons, so that and you have also all flavors. So it's not something like really a normal scattering in particle physics. It's really some kind of more, it's a change in the field configuration. So it's something a little bit more macroscopic, if you want. And that's also why we are not really able to see it so directly, at least so far in colliders. Of course, similarly, we had this non-trivial vacuum also for QCD. So in principle, we had also the QCD sphalerons. The QCD sphalerons are not so interesting because in this case, they would conserve the B plus L or B minus L number. So actually, the B number is the only involved. In the case of QCD sphalerons, what really changes is the chirality charge. And in that sense, this is, as you see here in this plot, you have left-handed fields transforming to right-handed fields and similar. But in that sense, this would not change the baryon number. Okay, so given this additional B plus L violation, we have practically to revise a little bit the Sakharov conditions in the sense that we have, we can require B minus L violation, or, and this is the other choice, have the B plus L violation at the electroweak phase transition to really produce the baryon symmetry. And this is more connected to the electroweak baryogenesis we see in a minute. Of course, we need also C and CP violation, and the CKM matrix is also usually not enough to really produce large enough baryon asymmetry. So we will see it in a minute. We need usually additional phases, additional complex couplings in order to have a sufficient baryon number produced. And then, of course, again, we have this departure for thermal equilibrium, and there are different ways to produce it. One is exactly due to a phase transition, and this is with the thing we'll discuss in a minute. Or the other way is to have a particle which is out of equilibrium when it decays, and this is on sense more the leptogenesis direction. Let me go to the electroweak baryogenesis case. Yes, so for the electroweak baryogenesis, we can see that actually we can satisfy all the Sakharov conditions also within the standard model, in the sense that we have the spalarons violating the baryon number. We have a C and CP violation from the weak interaction and the Yukawa coupling. And we have in principle, we could in principle have a departure from thermal equilibrium if we had a first order electroweak phase transition. So this one was in the 1985 proposed by Kuzmin, Rubakov, and Shaposnikov as a way to produce the baryon asymmetry at the electroweak scale. And in that sense, it was very economical because you had just a standard model, and in some sense, it would have been really wonderful if this would have been worked. Now here I have just a slide describing a little bit what I mean with the first order phase transitions. As you probably all know, the phase transitions can be classified according to Ehrenfest depending on which quantities becomes discontinuous at the transition. And if you have a first order phase transition, then the first derivatives of the free energy are discontinuous. So the entropy is discontinuous, and then the heat capacity in some sense diverges. And this is, for example, of course, if you could have a second order phase transition, then the second derivative would become discontinuous. And the other parameters, in particular the entropy, would just be continuous, have just a kink. And in that sense, the order parameter in that then would change just continuously. And in that case, in some sense, the transition is going smoothly so that you do not really have enough departure from thermal equilibrium. Now, how do you see if you have a first order phase transition in the standard model? Well, in the standard model, what we know is that the field, which of course responsible for electroweak symmetry breaking, is the Higgs field. So we have to observe what happens to the Higgs potential. And generically, we can have a first order phase transition if we have a phase two phases coexisting. So in this sense, if we have, as in this case plotted here, the case where at the critical temperature, we have two minima, one at 0 and one away from 0, which have exactly the same energy. And then in some sense, going from one vacuum to the next, again, has to go through a tunneling process, which means again you have a discontinuous change in the order parameter, which is the vacuum expectation value. And in this sense, this would correspond to a first order phase transition for the Higgs field. Now, of course, you all know the Higgs mechanism. So we have indeed at t equal to 0 the Mexican hat potential as a shape. And the point, of course, is we have to add to that also the thermal corrections. So, of course, at t equal to 0, we know that the minimum is just at the non-trivial vacuum expectation value, but we need to explore what is the effect of having thermal corrections to the Higgs. Just another comment, if you have a first order phase transition, what really happens is, as I said, that you have these tunneling of from the false vacuum to the true vacuum. And what it happens in cosmology is that you create bubbles. So you have bubbles of true vacuum within the false vacuum, and you have also bubble walls. And the bubbles usually then tend to grow because the true vacuum, of course, is energetically more favorable than the false vacuum. And at a certain point, you will have also practically collisions on bubbles against bubbles. And if this process is sufficiently violent, you could also produce not only baryogenesis, but also gravitational waves. And this is indeed one of the additional signatures that you could hope for in the case of a first order phase transition. Now, how does baryogenesis happen in such a bubble or in such a case? Well, the baryogenesis actually happens mainly at the bubble wall, more or less. So you have a bubble of the broken phase, and inside the bubble, the spalaron processes are practically switched off. You have, in principle, therefore, no chance to change the baryon number inside the bubble. But what happens instead is that you can create a net baryon number inside the bubble by having a different, if you want, transmission and reflection probability of fermions at the bubble wall. And in this sense, the bubble wall is also what provides, if you want, the CP violation. It can happen in different ways. You can have it just by, for example, complex phases, also in the masses, but you could also have it from the vacuum expectation value of the Higgs, for example, in the 2 Higgs doublet model, that could be complex. In that sense, therefore, the behavior of particle and antiparticle at the wall will be different, so that you have, if you want, more baryons can come into the bubble than antibaryons. And outside, where you are still in unbroken phase, the spalarons are still active. So outside, if you want, even if you have an additional abundance or overabundance of antibaryons, those are actually cancelled, if you want, by the spalarons, which are still active. So in that sense, at the end, you are left just with a baryon number inside the bubble, because the bubble at the end will take over, of course, the whole universe. I mean, this one you can do also more quantitative, and what people usually do is to consider the quantum transport equation of the fermions across the bubble wall. Of course, it's usually easier to do it in the frame of reference where the bubble wall is at rest and the quarks, for example, scatter on the bubble wall. And again, this in some sense is a similar quantum process as, so again, it's a quantum mechanical process, and you have again a different probability of transition and reflection for the different states. And in that sense, you have you are able, therefore, for example, to have an overabundance of one state or with respect to the other inside the bubble. Notice, of course, that the fact that the fields propagate differently is also connected to the Higgs vacuum expectation value, because the Higgs vacuum expectation value, of course, changes from different from 0 to 0 in the bubble wall, because that is exactly what defines the bubble wall. And here, for example, is just the expression where you see that you have a CP asymmetry practically on both sides of the wall, and you can get also the baryon asymmetry very near to the wall. And this is exactly what gives you the baryogenesis. Now, in order to have these, you need, as I was saying, really to form a bubble wall, so to have a first order phase transition. And in order to see if this is possible, one has to look at the effective potential for the Higgs at finite temperature. Now, here is just the schematic form of this potential. You see that you have, as usual, the mass term, the quartic term for the Higgs, but in this case with masses and coupling which are temperature dependent. dependent. And then there is also an additional term, which is this cubic term with this coefficient E of t. And this cubic term is the one which actually give rise to the barrier. And these contribution to this E of t are coming mostly from bosonic loops, so that the presence of a lot of light bosons increases the strength of the phase transition. Of course, one has to be a bit careful in computing because these computations of the effective potential are actually not really trustworthy at the critical temperature. So for really seeing that region, you need to go to lattice computations because if you want so the perturbation theory breaks down at the phase transition. But nevertheless, if you would find out that the transition is sufficiently strong, and this means that the vacuum expectation value divided by the critical temperature has to be larger than 1, then you could be able to produce a baryon symmetry at the electroweak phase transition. Unfortunately, in the standard model, we have a Higgs which is too heavy. And so if you look at the phase diagram for the standard model, you find out that you would need a Higgs much lighter in order to have a first order phase transition. And we are instead in the region, so now we know that the Higgs mass is 125 GeV, so we are in the region where we have a smooth crossover. And this, for example, on the right is the plot of the vacuum expectation value divided by the temperature as a function of the temperature. And you see that it changes continuously, and that the phase transition, it's, you have a continuous change of V, so that you are not in a first order, but in a second order, or even a crossover, actually. So in that sense, the standard model doesn't really give you electroweak baryogenesis. Yes, so that is just my conclusion. So the standard model, unfortunately, is not able to provide first order phase transition, but of course you can do change it. So in some sense, you could add additional particles, or you can modify the standard model and allow for a first order phase transition. And this also has the advantage often to also be able to add additional CP violating phases. Because another thing I also should mention, in the standard model, apart from the fact of the phase transition, also the CP violation is probably not sufficient because, I mean, usually again, you have only the CKM as a possible source. Now, as I was showing you, the key parameter or the key term which can make the transition stronger is this cubic term. And therefore, this cubic term is counting in some sense bosonic degrees of freedom. So it's clear that one way to increase the strength of the transition is to add additional scalars. And one way to do it is just to add additional Higgs. For example, consider a 2 Higgs doublet model. Another way to add a lot of scalars is actually supersymmetry. If you have supersymmetry, of course, there also you have a lot of scalars, many of them even colored. And in particular, the superpartner of the top, which is, of course, directly connected with a large coupling to the Higgs. And that correction is actually one which could give you a first order phase transition. And finally, you could also add additional higher dimensional operators to change really the Higgs potential by higher orders. And these also can give you a phase transition which is of first order. So in that sense, you have many possibilities. In that case, though, you are changing really the potential, and you would also have different couplings compared to what you or what you hope to measure, of course, in the at colliders. Okay, so let me go to the simplest possibility, which is probably electroweak baryogenesis in a 2 Higgs doublet model. So you have a second Higgs doublet. Here I am parameterizing in this form, and of course, again, you have 8 degrees of freedom, 4 in the first Higgs doublet and 4 in the second Higgs doublet. And 3 of these degrees of freedom are Goldstone bosons, and they are absorbed by the gauge fields, and they make the W plus minus and Z massive. But of course, you are left then with 5 degrees of freedom, which are physical. In particular, the one who plays the role of the standard model Higgs, but you have then heavier Higgses, pseudoscalar Higgs, and also charged Higgses. And these, of course, can play a role not only in the phase transition, but also in loop diagrams. In particular, you can have, for example, the exchange of a Higgs, giving you also contribution to electric dipole moments. Now, for the case of the 2 Higgs doublet model, you see here, for example, the potential. This is one example. I didn't write all the couplings. In principle, you have up to 7 even quartic couplings. But you see immediately one possibility that you already have a phase, an additional phase in the mixed term between H1 and H2. And you can also have a phase connected to the fact that the vacuum expectation value of the second Higgs can also contain a phase. So you have automatically additional CP violation, which can allow to have baryogenesis in some sense more easily. And here I have stolen a slide from Stefan Hubert from a talk some time ago, where he described what they found, exploring exactly this model, where they had this phase between the Higgs webs, which changes along the bubble wall, giving rise to a source, if you want, of CP violation in the bubble wall. And on the other hand, the EDMs were connected more to the other phase, the phase that you had in the potential, so in the mu3 term. This was the phase 5. So in that sense, in this kind of model, you had you could predict both the baryon asymmetry, which is exactly these curves with the eta here, which are highlighted. And here you have eta b in units of 10 to the minus 11. So this value of 40 or 60 is actually the one you need. And then you have also the possibility of predicting the dipole moments, which are of the order of 10 to the minus 26. So they can be, depending on the phase, in these ballparks, so they could be practically observable very, very soon. Note that in this case, and this is exactly also what I'm come here, so if you look at the electric dipole moments in this model, actually the one loop diagram is not the dominant one. The ones which are more important are the diagrams which involve instead these additional loops, so 2 loop contributions, which involve also in some cases, well, the one in the middle would involve QCD couplings, and this would give you a kind of similar operator for QCD, but of course also the last one has instead also the photon. And this 2 loop diagram is actually are dominant compared to the 1 loop. And here you can see that the values, you can predict both not only the neutron electric dipole moment, but also electric dipole moment for Mercury. And also, I think the first one is the electron. So you find that for phases of the order of 0.01 or 0.1, you could have practically observable EDMs. Now, let me go then to the other case I just mentioned, the one connected to supersymmetry. As you probably all know, supersymmetry, of course, doubles the degrees of freedom, and for every fermion you have a boson and vice versa. This means, of course, that you have a lot of bosons which would contribute to the Higgs potential. And in particular, as I said, the superpattern of the top is the one which is actually more important for the phase transition. And as I said, the stops in supersymmetry, if they are sufficiently light, they could increase this cubic term. And but you could also do it in different way. If you do a SUSY extensions, you could also use singlet or other extension beyond the minimal supersymmetric standard model. So you also have any additional CP violating phases in the supersymmetric sector, because you can have again have a phase on the mu term, which is the mixed term for the Higgses. But in this case, you have also phases connected to the gaugino masses and also the trilinear terms in the superpotential for the scalars. At the beginning, people explored, of course, this model for relatively light Higgs, when the Higgs was found to be 125 GeV, it was not completely clear that that could be accommodated. And the group of Marcela Carena et al. Found out that actually if the quarks are sufficiently heavy, you can actually arrange to have a first order phase transition with the Higgs at 125 GeV. But you need the stop to be relatively light. And at that time, of course, it was still a possibility. And I will get to that in a minute. If that is still possible, probably it's not so easy to get. There are other scenarios, though. There is also the possibility of having, for example, the Beano to be really the responsible of electroweak baryogenesis. In this case, there is really a phase in the Beano mass matrix which is connected to baryogenesis, and this in some sense is a bit the extreme case, because in that case the contribution to the EDMs becomes the smallest. And in these two plots, actually I didn't write it, I should have written it. On the left you have the electron dipole moment, on the right you have the neutron dipole moment. And in the green area, so this green line is exactly giving you the line where you have the correct baryon asymmetry at from electroweak baryogenesis. And you see that in this case, you can go down also for two phases below 0.1, and you still obtain the correct baryon asymmetry if the mass of the Beano is relatively light. Of course, here it's on the 200 GeV, which is still not completely excluded. Note that here is just a pure Beano, more or less. So it's quite difficult to measure it at colliders. And you see here the contour plots of the prediction for the neutron electric dipole moment. You see that in this region with the 200 GeV Beano, you can go down practically one order of magnitude from what you would expect and what you have in other models. Still, also in this model, to have the phase transition to be sufficiently strong, you need to have a light stop. So this is unfortunately more and more difficult. So here you see the plots of the limits on the stop mass, which seems to exclude practically all the area where the stop is light. Light means lighter than the top. Of course, in these areas where you have degenerate top and stop, it's always a little bit more difficult to do the analysis, but nevertheless now the collaboration have been able to more or less exclude, and you have here just the region. So you are practically, you need to be above 200 GeV nearly. Yeah, so actually even more. There is here, yeah, of course, this depends also on the mass of the Beano, as you see here. So in that sense, you could still be maybe in the region where the Beano is a bit heavier and still have a light stop. But then again, in this case, then you would have actually a prediction for the neutron dipole moment, which is quite stronger. Okay, of course, this was a discussion with minimal SUSY, and we can go beyond that. So it's not clear that you have to be in the minimal supersymmetric standard model. You can have singlet fields also in the standard model. You can have also singlet field without supersymmetry, so in that sense. And in that case, you have more phases, you have less constraints, and yeah, and you have in that sense more possibilities, of course, which I'm not able to go to and describe all here. So in that sense, I think the exploration of the EDMs is one additional important signature that one would expect to see in the case of electroweak baryogenesis. And if the future experiments exclude, give exclusions stronger and stronger, these will also go along the direction of excluding electroweak baryogenesis, at least connected to Higgs doublet or supersymmetry. Note, just as a last comment, you could have also something like a cold electroweak baryogenesis, just as I mentioned. And in that case, it's something which happens after inflation. So it's a little bit working in a different way. And in that sense, some of these constraints on the first order phase transition are much weakened, because in that case, in some sense, you're not in thermal equilibrium. So it's not a phase transition in equilibrium. And you have a little bit more freedom, just as I mentioned here. So in that sense, it's not always needed to have actually a thermal phase transition. Okay, another possibility, of course, in supersymmetry is still also to have baryogenesis via the decay of a supersymmetric particle. So this one would be more in the direction not of having the phase transition, but having the out of equilibrium decay of a particle. And this is also a scenario we explored a few years ago. And in that case, you have, for example, the possibility to exploit the decay of the BINO through R-parity violating coupling. And R-parity violating coupling are automatically giving you baryon violations. So in that sense, you can produce directly the baryon asymmetry. And you do not need, in some sense, the sphalerons to move baryon and lepton number around. So you can produce, for example, this baryon asymmetry also after the electroweak phase transition, if you want, because you are producing directly the baryon asymmetry. And in this case, we had found a way where we could produce this baryon asymmetry at the same time also as a density of dark matter from in this case, gravitino dark matter. And the advantage was that we had relatively naturally orders of magnitude of densities in baryons and dark matter of the similar order due to the fact that they were produced by the same particle, and the fact that this CP violation parameter was similar to the branching fraction. Okay, and this is all I wanted to, so I had more slides on this, which I took out because at the end, this is one particular scenario. And the only thing which is a little bit disappointment in this scenario is that the masses of the particle involved has to be pretty large, which means, for example, that even if this coupling, of course, can give you contribution to electric dipole moments, the particle, in particular the quarks, are so heavy that this is practically difficult to see. Is there a question? So,
все ребята делают вид, что понимают.
Согласованно здесь надо.
Okay, so I stop here about the part of baryogenesis. So if there are any questions, please.
I have a simple question. Again, this is Takashi from Osaka. So in the beginning of this section of the electroweak baryogenesis, you only discussed on the first order phase transition. Is there not a possibility of using second order phase transition? For example, using the different expression of this potential?
No, if you have a second order phase transition, you cannot really, the electroweak baryogenesis doesn't work. So you need this bubble wall. So I was, as I was trying to argue here, you need really to have a non-trivial bubble wall, which gives you sufficient separation, if you want, between particle and anti-particle. So if you have a second order phase transition, there is no bubble wall. So the parameter here, the change, if you want, is more continuous and less abrupt. Okay, so you would not really produce bubbles in the universe. You would have a kind of smooth change everywhere of the vacuum expectation value.
I see. Okay, thank you.
So in that sense, you stay in equilibrium all the time if you want, and therefore you cannot produce the baryon asymmetry. Okay, more questions? Okay, I don't see any. So, well, okay, so let me go to the last point. I see that I am also actually more or less on time, or even the last part will be a little bit faster, but then we will have also time for questions at the end. So let me go to the axions. Yes, so in that sense, I hope I convince you that in order to have baryogenesis, especially certain types of baryogenesis, we will need to have additional phases, and these phases show up also in the EDMs, not only the neutron EDMs, but in principle generically also electron EDM and also other mercury EDM, etc. So as I mentioned before, you could also do baryogenesis via leptogenesis. In this case, in some sense, the CP violating phases are more connected to the leptonic sector, and therefore you would expect to have a more quadratic connection to the electron EDM. But even there, I mean, it depends, of course, on the case. In some cases, the contribution is not. If the right-handed neutrino are very heavy, it's quite difficult to see them. But now, let me go to the other side of the CP violation. So in particular, the strong CP violation that we also discussed. So we had this theta bar parameter, which gives you directly a large contribution to the neutron EDM. And from the constraints we have from exactly the neutron EDM, we know that theta bar has to be less than 10 to the minus 10. So as a theorist, I don't like to have small parameters. So we all, as a community, do not really like to have a small parameter without having a clear explanation why they have to be so small. And one possibility, as I already discussed, is the fact if you have a massless quark, then you could, in principle, just get this theta bar to 0 without having any physical consequence. But this seems not to be the solution in the standard model. So already at the beginning, when this problem was found out, there was another solution proposed by Peche and Quinn. So Peche and Quinn proposed to add a new chiral symmetry, chiral global U1 symmetry, and break it spontaneously at the high scale. Well, actually, at that time, it was not a very high scale. It was actually electroweak in the original model. And then you can, again, in some sense, transform this theta bar parameter into a dynamical parameter. So in that sense, you have exactly this term, which I'm writing here. So the same Lagrangian we had before with GG tilde, but this time multiplied by the axion field and not the theta parameter. So at the end, theta bar plus the axion field over FA is what, if you want, the physical theta term. And the axion can, in some sense, cancel this theta bar parameter and relaxing to the value such that theta total is equal to 0. Now, Peche and Quinn did not realize in the original paper that the fact that you can relax this theta bar also means that you have a degrees of freedom, which is this pseudo-Goldstone boson A, and this was realized immediately later by Weinberg and Wilczek. And this pseudo-Goldstone boson, of course, has also other, if you want, consequences apart from canceling the theta bar term. In particular, that was also realized pretty soon, is that the axion is again a pseudo-Goldstone boson, so it has exactly the same quantum numbers of the neutral pion, and therefore it mixes actually with the neutral pion, so that at the end, if you would have this pseudo-Goldstone boson at the electroweak scale, you would have actually changed also the phenomenology, and in that sense, it was therefore immediately excluded to have this axion at the electroweak scale. What you can still do instead is to have this axion at a different scale. So if you choose this FA scale, which is in some sense the decay constant for the axion to be much larger than the decay constant for the pion, then of course the mixing will remain small with the pion, and you can still have this as a viable field. And in particular, this field is very interesting from cosmological perspective because it can be a pretty natural dark matter candidate. And the characteristic is that you don't need to do a lot to produce, in some sense, dark matter in the right abundance from this field. Because you have just by construction what is called the misalignment mechanism. So the idea of the misalignment mechanism is the fact that this field is, of course, massless originally, because you do not have still, before the QCD phase transition, there is no contribution to its potential from if you want, from the instantons. And therefore, it's a very light field, it's massless field in cosmology, and it can be in some sense at any value in the field space. Then after the QCD phase transition, you obtain a potential for this field from instanton effects, which is of course, the scale is coming from lambda QCD, and the shape is just a cosine type of potential due to the structure of this GG dual term. And you see here, you have a cosine of theta or theta bar plus this A plus FA, so that the axion relaxes, so the minimum of the potential is exactly corresponding to have a full or effective theta term, which is 0. So what happens is therefore that the axion oscillates around this field value, and luckily, in some sense, the axion is actually can decay through into 2 photons, for example, similar to the pion, but it has a lifetime which is so long that is actually this oscillation of the axion lasts much longer than the present age of the universe. This means that if we had this possibility of the axion starting from any value different from 0, it would still be oscillating now around the minimum. And of course, if the axion oscillates around the minimum, the average theta angle is 0, but still you have a, if you want, a condensate of axions which oscillates around this minimum. This condensate, you can view it as a kind of zero momentum particle, so it looks like a cold dark matter component. There is no free streaming, and this would exactly be what you need in some sense to describe a cold dark matter component. Now, you can do even better. You can actually compute explicitly what is the density of this field given the initial condition. So you have to take into account that the mass of the axion is also in some sense temperature dependent. So it will start to grow at the QCD phase transition. And yes, and then you can follow. So here, for example, some of the simulation from this paper by Arvanitaki and Dimopoulos, where they really, you see the oscillations of the field at the end and the different initial condition. Now the potential is not exactly quadratic. Of course, it's a cosine potential. This means that if you start the oscillation very near to the maximum, then you have to you start to feel that the potential in some sense is deviating from quadratic, and this is what is expressed by this P of theta, which is this plot on the right side, which in some sense gives you a correction of your density depending on the initial condition if you do simulations away from the quadratic, if you want, potential. Usually the first computation were done considering just an m² phi² potential, because of course that is simpler to treat. So, but as I said, you can do simulation also including these non-harmonic effects, and you can compute what is the density in the axion. And you obtain this omega h² of axion, which is proportional to the initial misalignment angle squared, and also proportional to this FA parameter. So you need a relatively large FA in order to be able to have sufficient dark matter into the axion. Of course, there is a kind of degeneracy between this theta angle, the initial misalignment angle, and FA. And for this misalignment angle, you have different scenarios, because of course you could be in the case where you break the Pechequin symmetry before inflation. If you do that, you would assume that in some sense you have the same value of the theta parameter, the initial angle, if you want, for all our visible universe, because you broke the symmetry and you are in some sense before inflation, and then when you expand or inflate the region, you inflate a region where the theta parameter was equal. And in that case, of course, you have a strong dependence on the initial condition. Depending on theta, you can have densities which change a lot. Of course, the natural initial value would be a theta of order 1, since the parameter, of course, the axion is, if you want, an angular variable, so it can be in the range between 0 and 2 pi. And this is the range also of theta. And this means, yeah, theta of order 1 would be a kind of expected value. And theta very small, it's if you want at the cost of some fine tuning of the initial conditions. But there is also the other scenario, which is the scenario where you break the Pechequin symmetry after inflation. If you break the Pechequin symmetry after inflation, you would actually have, in some sense, different domains formed with different values of theta. And in that case, what is really setting the density of the axions is more an average value of theta within all these fractional domains. And in that case, also, you can produce also topological defects, in particular axionic strings, that can also give you an additional population of axions. So this computation is much more complicated, and there is quite a large uncertainty, so I don't give you the value here. But in this second case, you would have to take into account that there is also a possibility to generate axions, as I said, via topological defects. But generically, you see here that for if you assume a theta initial misalignment of order 1, you get more or less the right dark matter density with FA below 10 to the 12 GeV or so. On the other hand, for this parameter, you also have a lower bound coming from the cooling of stars and supernova. So indeed, if you have an axion, you would also produce it in every thermal bath, if you want, since this particle is very, very light. It can be easily produced from the internal part of the star or in a supernova, similarly to the neutrinos, for example, and it would carry away energy from the star and the supernova. So it will contribute to the cooling. And so if the FA is too small, the coupling is so large that you would actually change the evolution of stars or supernova. And this is the constraints of 0.5 10 to the 10 GeV. It was computed already quite some time ago by Georg Raffelt. Now, if you assume this value of FA, one has to say that therefore in the case of the QCD axion, you also know what is the mass of the axion. Because you have the relation from the potential we showed before. You see that here, if you expand to quadratically, you have a relation between lambda QCD and FA to give you the mass. And this is exactly the expression I give you here below. You see that for FA of the order of you need for having dark matter, you have, assuming theta of order 1, you have a mass of the axion of the order of 6 10 to the minus 5 electron volts. So it is quite a very small mass. And this is in some sense what is usually called the axion window. You can see it more clearly here in this plot, where on top there is exactly this parameter FA, and the bottom you have MA, so the mass of the axion, and you have the constraints in blue. So these are practically all the constraints which comes from, as I said, the cooling of supernova, of white dwarfs, etc. You have also some constraints from cosmic microwave background and Big Bang nucleosynthesis due to the number of degrees of freedom. Again, the axion is very light, so if it is produced thermally, for example, will contribute to the relativistic degrees of freedom. But these, as you see, these limits are for very high masses because there you would also have a kind of thermal population. Instead, for the very small masses, you see in red, the regions corresponding to the post-inflation Peche-Queen phase transition or the pre-inflation Peche-Queen phase transition. And you see clearly that in the case of the pre-inflation Peche-Queen phase transition, you could in principle go to even lower masses, assuming that you tune, if you want, the misalignment angle, theta I. And in the last line, you see a few experiments which are looking for axions. You see the ADMX experiment and the YAXO and other helioscopes, which look at different masses. And in particular, the ADMX is the only experiment at the moment which looks at the in the region where the cold dark matter should be. And indeed, one can look for the axions in different ways. Of course, the axion, as I said, similarly to the pion, has actually a coupling to two photons. And this is, if you want, generated by this triangle diagram, if you want, where you can have different particles in the loop, depending on the model of the axion. And therefore, you have a slightly different coupling GA gamma gamma. But if through this coupling, if you have an axion which arrives in a strong magnetic field, even a classical magnetic field, then the axion can oscillate into a photon. And this is indeed what is used in many experiments to try to measure the axion. For example, these helioscopes, which look at axion coming from the sun and transforming into a photon in a strong magnetic field. And as you probably all know, we also have other experiments which try to produce the axion also in the laboratory, which are connected more to having practically this transition twice. For example, light shining through the wall experiments like the Alps experiment at DESY, and also other experiments connected instead to the birefringence effect. So the fact that the polarization plane of the photon would change in some sense due to this transition to an axion. But probably for this audience, let me first show a little bit of these constraints based on this coupling, the A gamma coupling. You see here some of the experiments. This is a little bit actually not incredibly new. I apologize. I had actually a better plot. I think I didn't include it, but I can show it later if you are interested. This is, as you see, there are quite, again, different types of experiments. And in some sense, these bands, which are here going from low mass to high mass with KSVZ and DFSZ as labels, are exactly the two typical models of axions that you would expect. And as I was saying, the ADMX, which is actually this pink region, is actually now trying to get to the dark matter region, which is at the order of 10 to the minus 6, 10 to the minus 5 electron volt for the mass. And yeah, here it's actually a bit more new figure from ADMX. But of course, as I said, this audience is probably more interested to other couplings. In particular, of course, you have still the coupling to nucleons because you are generating, if you want, the EDM from the theta term, as we saw. But now, instead of having the theta term, you would have the axion actually coupling to the nucleons and giving you, if you want, oscillating EDM. Indeed, we expect the axion to oscillate with a frequency which is the mass of the axion divided h bar. And these will exactly feed into this EDM of the neutron and also other objects, so that you would, in principle, have a time-dependent EDM. Unfortunately, this mass scale is or time scale is pretty small, so it's actually, yeah. So there are some experiments trying to look at it. You probably know about them more than me. But it's not so simple in the sense, of course, on average, these would be actually zero. Another type of experiment, and I guess maybe also there you will hear more about it, I guess, on Wednesday, is the fact that you could also have an effect connected to the derivative of the axion field. So the axion fields as pseudo-Goldstone bosons have also derivative couplings with the fermions. And in that sense, these kind of derivative coupling would also generate so a kind of magnetic field connected to the axion, or the fact that the axion is not constant. Indeed, since the Earth is moving within the halo, you would expect to have a non-trivial also space dependence for the axion field. And therefore, you could have an effect which is called a kind of axion wind precession. And this is what is actually planned to be observed by Casper. So as I said, I think probably on Wednesday, you will also hear something about this as well. And of course, you don't always have the coupling with the neutrons. You also have the coupling to the electrons, and the coupling to the electrons would allow you also to give you something like a axioelectric effect. So you could absorb an axion in an atom and emit an electron, for example. So those are all different couplings which one could explore. And of course, in particular, the one of the oscillating EDM would exactly be one-to-one connected to the dark matter behavior. So in that sense, that would be really a smoking gun, saying that we have actually, at least it would allow us to measure more or less the component, the dark matter component in axions. Because this is another thing, of course, I have to mention. It should be clear that these population of axions could be there even if its density is not large enough to be the dark matter. This is, of course, because this misalignment mechanism, it's pretty generic and would work practically for any mass of the axion. And therefore, I mean, you could also be that we have a component of dark matter in axions which is less than the total dark matter density, but still, for example, giving you a signature, for example, in oscillating EDMs. And in this part also, the other comment I have here, of course, I concentrated on the QCD axion because the QCD axion has this direct connection to the theta term and therefore to the neutron EDM. But it should also be clear that in principle, you could have also more generic particles like what are called axion-like particles. Axion-like particles do not absolutely have to solve the strong CP problem. So in some cases, they do not couple to QCD, or they do not couple exactly with the same strength, if you want, to the GG dual term. But they could also nevertheless be present, and they could have more generic couplings, of course, both to photons, neutrons, and electrons. So in that sense, I would also say that even beyond this axion window, one could have some possibility to observe an axion-like particle in these different experiments. Okay, now for regarding the axions, here I have just together a couple of summary. There were also some other signature which people proposed for the axion. Sekivi some time ago proposed that actually you should also see these axions because you have caustics in the distribution of the cold dark matter in the galaxy. In principle, you could also see the decay of this dark matter candidate. Unfortunately, in the region where it should be the dark matter, the mass is so small that the lifetime is more than 3 times the age of the universe. So in that sense, it will probably be hopeless. But on the other hand, if you have an axion-like particle, you could also be some other place in the parameter space. And of course, as I said, generically, you could have mixed scenarios as well, where you have not the whole dark matter into axions. So in that case, you could have additional particle, and here I was just mentioning supersymmetry because that would be natural, but there are also other possibility, other non-supersymmetric cases or non-supersymmetric candidates. Yeah, and also, yes, so that was exactly the final mention that you could also have other condensates which are not connected to the QCD axion, but they could also be part of the dark matter. And in that case, of course, again, different scenarios could also arise. Okay, so here I had a part on Affleck-Dyn, but I think I will probably skip it because I see that I am already at the end. So let me go to the conclusions. So here are my conclusion outlook. So I think in cosmology, we observe this non-vanishing baryon number, suggesting the need of initial CP violation. And as I tried to explain, the standard model does not seem really to satisfy all the Sakharov conditions. So we need to go beyond the standard model to add additional sources for CP violation. And these, of course, they could show up also in the electric dipole moments. At the same time, also the Peche-Quinn solution for the strong CP problem give rise to a very good dark matter candidate. And this dark matter candidate is again directly connected to the EDMs. So in that sense, this is another direction where cosmology and experiments on EDM could come together and give us a stronger, for example, as I said, a stronger footing about the role of axion as a dark matter. Now, the last part was more connected to axion and the generation of baryon asymmetry via axions. Actually, recently there have been a few papers discussing the possibilities. This was more in the direction of Affleck-Dyn baryogenesis, and also the direction of the fact that if you have a time-dependent axion, this would in some sense give you a source for baryons and for CP violation in the in your cosmology. So that is also a possibility. And in that case, then there will be again more tight connection between axions and baryogenesis, even if at the moment I'm not sure this will give you very particular signatures in the EDMs. And I think this is all I wanted to say. And I see that I am actually pretty much on time. So we have actually time for questions. So any questions? I don't see, let me check the chat, but I don't see it. No, I don't see anything in the chat.
I see one hand raised. Where is it? Philip.
Hello. Yes, my name is Philip. I had a question. You're probably aware of that the neutron EDM collaboration measured oscillating EDMs and set a limit which is above this classical QCD band of interaction strength and frequency or mass. And there's a discussion going on whether it's reasonable to actually search in that domain or whether kind of that's unphysical. Can you comment on that?
Well, I wasn't aware. So, okay, then I missed it. When was it? And which mass region was it?
Well, it's in the very low mass region. It was published in 2017. If you go to this, yeah, it's left of that exactly. It's kind of below there, yes. And it's
Yeah, maybe I didn't really see it because it's in some sense in that region it's very difficult to have really the dark matter in that field. So in that sense, you see that for this, or well, I mean, you have to leave otherwise with very, very tiny theta if you want the initial angle.
Okay.
You see that the density goes becomes larger and larger. The larger is the Fa, or the smaller is the mass.
Yeah.
So in that sense, you in order to have that to be really the dark matter, you would need a very tuned initial condition.
Yes, yeah, so my question was going somewhere else. So on your slide 64, I think you showed this kind of mass versus general coupling, not the coupling which has a strict relation to the masses here. Yes.
This one?
Or yes, and there's, so to say, so there's all this space above the band which is KSVZ or DFSZ.
Yes.
Yes, and if one searches for axions in this upper part, so to say.
Well, in that upper part, they cannot be really the QCD if you want axion. So
Okay.
they would be axion-like. So you have actually the chance to be there. Actually, there is a well, I don't have the plot. I can find it in case. So there is, in principle, another band if you want, where axion-like particle can be dark matter, and this is actually higher. So it's more here.
So it's like the Casper experiment. They propose also to search in that band with an oscillating EDM effect or this axion wind effect.
Yes, but I think they are also in the mass.
Exactly, yes.
Yeah, exactly. So this is indeed, it's in some sense, I didn't concentrate on those because this in some sense is the mass range where now we do not think it's really the natural place for dark matter to be. Of course, as I said, for axion-like particle, you could probably, you have slightly different couplings, you could have more freedom. But for the, if you want to stick to the QCD axion, of course, these KSVZ, DFSZ are two different models, and so as you see, you have a little bit of change in the couplings. So, but still, this band you can, well, you could put a factor of 2 if you want to be really conservative, but you cannot move this band up very much. Actually, in some cases, it's easier to move it down because you can have models where you have a cancellation of the photon coupling in some way. Of course, that's also fine-tuned. So I'm not saying that it's something you would really like to have, but if you want to stay within the QCD axion, solving the QCD, strong QCD problem, the strong CP problem in QCD, you need to be more or less in this band.
Okay, thank you very much.
Any other question for our speaker? Please raise your hand. So I don't see.
Okay, good. So then hopefully everything was clear, and yeah, so I hope I didn't, how you call it, repeat too many things that you knew already. Yeah, so it's, as usual, that's a problem a little bit of doing virtual talks, that is difficult. You don't see really the people.
Yes. So, but on behalf of the audience, I would like very much.
Sorry, I would have a question. Because we have 4 minutes left, I think. You've been mentioning actually leptogenesis as a possible scenario for baryogenesis, and so there was this very interesting results, so preliminary results from the T2K collaboration, observing this CP violation in neutrino oscillations. How likely is it to answer this question of baryogenesis?
Well, unfortunately, there is no one-to-one corresponding to the CP violation at low energy and the CP violation in baryogenesis. So if you want, you can do, so there are different possibilities in practice. What you do especially if you do leptogenesis at high scale, you have many more parameters than what you see and you can measure at low scale. And in particular, there are different possibilities to produce also the baryon asymmetry, for example, or the lepton asymmetry just from the Majorana phases. And in that case, of course, the Majorana phases are not what has been measured by the T2K. So this is still the Dirac phase. So there are scenarios, you need constraint scenarios to have a relation between the low energy CP violation and the high energy CP violation if you want. So for example, if you try to have only 2 right-handed neutrino, or if you have a particular masses so that you can, in some sense, reduce the freedom that you would have. So at the moment, I'm not aware of, actually there were some papers by, I think the group of Silvia Pascoli, where they were trying to use just the low energy CP violating phases for leptogenesis. And I think in some cases they succeeded, but it's not the only possibility.
Okay, thank you.
Okay, we still have time for another question. Let me see.
If I can, sorry, I mentioned one thing. Actually, we also have, now that I think about it, we also have a model where we can do baryogenesis, leptogenesis via the Majorana phases at the low energy, but still you will not be able to measure it by T2K. You need to measure it by the, for example, looking at neutrinoless double beta decay in some sense. And also in that case, it's a model with only 2 right-handed neutrino and some constraints on the masses. So in that sense, it's also, again, a model where you reduce the number of parameters.
Okay, I don't see any more questions on the chat.
Okay.
So, well, thank you very much. It's very good that you did a very comprehensive lecture, and it's good that you covered the axion dark matter as well. Thank you for that.
Good. I hope that will be useful for the next days.
Yeah, it is.
Yeah. Thanks a lot for inviting me, and also for hearing my talk, of course, my lecture. And yes, so I will probably follow a little bit also the next part of the workshop to see what people are doing.
Good. So we reconvene at 2 o'clock for the workshop, or 5 minutes before, because Stephanie will do an introduction. And then for those of you who are only following the lectures, we reconvene tomorrow at 10:30. Okay. So see you this afternoon at 2. Bye.
Bye.
Bye.